expected him to pass the news.
If everyone can start making their way to their seats, please.
Ready, guys?
How you doing?
Looks like everybody's getting settled in, so I'll ask your attention here. Welcome you all to February's ASHRAE meeting. Thanks for coming out on a very cold night. February is typically our poorest attended ASHRAE meeting of the year, so thanks to all you diehards for coming out and making this one a success. And I'm confident that is tonight's presentation that drew you all here. Both to say, oh yeah, by all means, give it up. Both because you knew you were going to get a good show, and also because you all wanted to join me in wishing Darrell Boyce, a past president, as well as Don Weeks, and also past president, a very happy birthday. Colin Barry will be leading the vocals. He has a lovely baritone. He says no, he's under the weather. All right, but seriously, happy birthday, gentlemen. Coincidentally, both ASHRAE past presidents, both on the same day. That's great. First thing I will do, well, like I said, the next thing I will do is introduce our current board and executive. So most of them are here tonight. Richard Cameron is on the board. I didn't see him. Chris Frawley is here. Chris? Chris Fudge is here. Aaron Dobson. Dan Redmond. Adam Graham, our secretary. Abby Saunders, treasurer. George Momari, our president-elect. Rod Potter, our past president. And myself, Steve Moons, your current president. Welcome. I'll ask Adam to come up right now and introduce our guests for the evening and talk a bit about the seminar we have coming up next month.
Hello everyone. So first off, I'll rhyme off the guests that came out tonight. So we've got Michael Grant from Train. We've got Brenda Cleary at JP2G. We've got David Titus from Train as well. Colin Barry with Daikin Service. Rod Potter, Rodder CAS. Phil Brunet, MMM. Tom Armstrong, Stéphane Ripaud from Réglevar, and Gilles Lebrun, also from Réglevar. Heather Hain from Corrections Canada, and Jung Sang Kwan from Smith & Anderson. So thanks everyone for coming out. Forward to seeing more of you. And then I'll quickly just give you an update on the seminar coming up in March, on March 6th, 4th? Yes, 4th. So the seminar that's coming up is the part 2 of the hydronic system design or pumping seminar. Going a little more into depth than the last part, which is going to talk about different types of pumping, variable primary, primary secondary, get into heat exchanger design selection. So it'll be a good seminar, well attended. We still have some spots, so sign up now. The link is on the website. And if you have any questions, let myself or any of the board members know. All right, thank you.
Thanks, Adam. Normally this time we'd have Adam Moons, the membership chair, come and introduce the new members for this month. He's not here this evening, so I will take that on. We have 2 new members this month, Mr. Stephen J. Harrison and Mr. Yu Ma. I don't believe either of them are in attendance tonight, but welcome to our new members. I'll get George Mamari to come up and talk about the draw that he is running this evening.
Thanks, Steve. We got 2 tickets that we're raffling off for ASHRAE Research, donated by Long Hill Energy. There are 2 tickets for Ottawa, Calgary on March 8th. It includes a parking pass. I'll be going around the table and going to see you guys. Was that you got to win this time? So appreciate everybody who's donated so far. We're doing really great on the campaign. We're at 49% of our objective. So calling campaign's going to get probably started within the next couple of weeks. So look forward to getting a call from one of our committee chairs. Thanks a lot, guys.
Thanks, George. And thanks to the Long Hill guys as well. It's donations like that that really go a long way to getting our research promotion goal achieved. There are tickets that come to us free of charge. The company bears the cost of them, and we're able to profit all the proceeds that George bugs you guys for. So thanks again to the companies that have donated before, Engineered Air, SK Sheet Metal, Walmart. I'm sure I'm forgetting somebody, but it's great support that we get for our research promotion. Next we'll get Joe De Laval to come up and talk a little bit about the YAY event that he is planning, and also speak to the career fair we have coming up next month.
Thanks. For everyone, next week on Thursday, we're going to have a YEA event at Tailgaters again. For those who don't know where it is, it's on Maryville at the Maryville Mall, just across from Maryville High School. It's going to start at 5:30, go till 11. It's a $5 entry. Pool and appetizers will be included in that. It was a great time last time, and I think everyone enjoyed themselves. And if you want to try and meet me at pool, go ahead. Any challengers, come on out, because we're looking for as many people as possible. And Adrian's not here today, but I told her I'd do this for her. So the Student Career Fair is on March 3rd. It's from 3 till 6. We already have about 8 or 9 booths signed up for, so it's good attendance so far. But if you want to join, it's going to be at Carleton University in the Fen Lounge. It's $200 per booth. You can also get an advertising for a less amount if you want to do that route. Anyway, hope to see everyone out there. And if any students you know of, they want to talk to me and get more information, I'd be glad to help out. So, thank you.
Thanks, Joe. I know we do have a few students here tonight, and I'd encourage you to talk to your classmates and anyone else who knows students in the industry to encourage them to come out. It's really a win-win both ways. Suppliers, contractors, consultants, everyone gets a chance to demonstrate what they do in the industry and hire some good quality people who are graduating, coming on, and also gives the students an opportunity to explore what opportunities might be available to them in the industry. So it's not a lot of money, not a lot of time, but it goes a long way. So get in touch with Adrian Matani or anybody on the board to get more details if you haven't yet. Next we'll get Dan Redmond to come up. This month's theme is CTTC, Chapter Technology Transfer Committee. one of the main components to that is the awards that were given to local consultants for various projects, and it's really a lot, it's, I think, maybe a little bit more intimidating than you might think. So Dan's going to run you through how to get applied and potentially get an award.
Okay, thank you. So we just wanted to give a very brief overview because realistically I think a lot of people don't understand how easy it is to apply. I'll start starting. So, Perfect. Okay. So realistically, very briefly, the ASHRAE Technology Awards, I mean, the whole goal here is to recognize you for your everyday efforts, for the effort, the innovation that you put into your designs, your projects, and just earn some recognition, show off. There are 3 different levels for the competition. There's the chapter competition. Those who succeed and win at the chapter level then go on, or have the chance to go on to compete at the regional level. Those who win at the regional level have the chance to go on to the society level. Now, why bother? This is your chance to show off. This is essentially a chance to get some free PR. What client of yours would not be happy to know that you have won an award for the innovation that you brought to the team? And best of all, this is free and it is really, really easy. There are really only 4 requirements. You need to be an ASHRAE member. Most of the people, by being here tonight, are already in that category. You need to fill out what they call the short form application. It is that. It is short. It is 1 page. It is, I think, more complicated to renew your annual dues. You need to write a brief narrative. Now, brief, it's a maximum of 2 pages. There are 6 criteria that you should touch on. I'm not going to go into detail on those though. I'm trying to show you how easy this is. A system diagram also helps. So all in all, we're talking about a total of 4 pages. The only other requirement is a minimum of 1 year of successful operation for the project you're building. So the short form, that's it. There are 19 different categories, which means that we can give out 19 different awards. There are a lot of awards up for grabs, and we encourage people to apply. Deadline for applying is March 20th, so you have a little over a month. And if you have any questions, please feel free to contact myself or Michael Grant, who's from Train, seated over here, or Andrew Duma from Total HVAC. One other item just before I leave you all, we are also putting on a webinar in April. It is free. We encourage people to attend that also. There will be professional development hours. You can get up to 3 hours for people who are trying to maintain lead designations or other sorts. And again, any questions, please give me a call. Thank you.
Thanks, Dan. One other thing I'll mention about those awards is while typically we've received applications from consultants, you needn't be the consultant to apply for this award. So if you are a contractor or a supplier or an owner of a particularly innovative or interesting project, feel free to get in touch with the rest of your team and arrange to have this application put together. So like Dan said, an excellent opportunity to showcase some of your skills and increase the recognition of our local chapter too. Thanks. The last thing we'll do before dinner is we'll run through our tabletop displays. The first one I'll ask Chris Fudge to come up from Master Group. He's representing NAD Klima, is, well, let him tell you about it, grills and diffusers of a specialty type.
Go on.
So the key here is...
Thanks a lot, Steve. Master Group is proud to say that we're the exclusive distributor of NAD Klima in Eastern Canada. For those of you who may not know, NAD Klima manufactures high induction diffusers. So their diffusers can be used to achieve high levels of thermal comfort in a space. They can also be used to achieve additional energy efficiencies in your design. So keep it in mind, give us a call if you'd like to discuss it further. Thank you.
Thanks, Chris. And our second tabletop is Alex Demisi to come up with their solutions with Fujitsu variable refrigeration flow systems.
Thank you, Steve. Good evening. My name is Alex Demisi. I'm from Air Solutions. I'm the Air Manufacturers Rep, and we are representing Fujitsu Airstage variable refrigerant flow. We have extensive lineup from 6 to 24 tons, heat recovery and heat pump. If you have any question, any comments, or if you have an existing VRF project, I'd be more than happy to send you some information in the back chat. Thank you so much.
Thank you. So both the tabletops are to my left where we had the pre-dinner social. The guys are going to be around afterwards as well, so if you have any questions, flag them down. They're happy to help you out. With that, we'll adjourn until after dinner. Enjoy your meal. Daryl was good enough to mention, for those of you who don't know, I'll take a step back. Daryl's been involved with ASHRAE for 35 years and more. That's part of the introduction when he gets to his main topic. But one of the things that he's worked his way up to as far as being a chapter president, a director at large, regional directors. Daryl's now one of 2 or 3, I can't recall, one of 4 vice presidents in the ASHRAE Society, so just one step below presidential level. So an assassination attempt away, and Daryl's your man. But in all seriousness, Daryl's been an ASHRAE member for a really, really long time, and so part of his role this year, being a vice president, he has a bit of a presentation, and it's just a bit of an additional mealtime entertainment. He's good enough to give us a quick rundown on a little bit about what he's been doing for his vice presidential role. So with that, I'll let him take it over.
Thank you. Everybody hear me? Yeah, I have to hold up this far again. So what I'll do is give you a little update on the society and some of the things that happened this year, and a couple of which happened at the winter meeting. So as a society vice president, I do represent the society in a number of regions. But one of the big things that happened this year that's really a change in the direction for the society and the Indoor Air Quality Association. Those 2 associations began discussions. Don Weeks was a major player in this decision to move forward. We agreed in principle to join forces, and IA2A become a part of ASHRAE while maintaining its brand and its own board of directors. And we actually had votes, both our board of directors and their board of directors, during the winter meeting, and the 2 organizations approved this merger, basically. So ASHRAE will be operating the organization for IA2A, and it'll begin the process of strengthening the programs for ASHRAE and IA2A in the areas of indoor air quality and the built environment. So it's a major step in the right direction from my point of view. The other thing that's going on this year, and the board actually approved the strategic plan in June of 2014, and it's basically built around connect, educate, extend, and adapt. Those are the themes of the plan, and there are actually a number of initiatives that relate primarily to the regions and chapters. And one is that officers and board of directors will meet with some of the key business organizations and talk to them about the support for ASHRAE and what it means to the ASHRAE members and to their organizations. I was personally one of the people that went to visit Carrier Corporation at their head office, and we had some very useful discussions, and I think we're strengthening our relationships with those major corporate organizations. We want to conduct 20 visits annually with consulting firms by the officers and board of director members to talk about support for those firms and the consulting engineers. And the council I'm specifically involved with, which is Pub Ed Council, is working more aggressively to pursue HVAC and art training for university students. It's something that was much stronger many years ago, and then it sort of dropped off. So we're trying to find ways that we can help support a better education program in the universities for HVAC and art. Promote the creation of student brands globally, increase use of ASHRAE publication, ASHRAE handbook, and curriculum. And so we'll be having some meetings going forward to see how we can actually support that important initiative. Initiative 2 is form an ad hoc committee to review opportunity to streamline procedures and more effectively utilize volunteer resources. And this is across the society. I have charged as the chair of Pub Ed Council all of my operating committees that report to the council to really look at the way they're using volunteer time. Are the volunteers feeling good about it, or do we have too much red tape? What are we doing to make this a very enjoyable pleasure experience while they do the great work that they do for society? Under Initiative 3, we're going to develop market-ready software, tools and apps for consulting engineers and other key constituents to use in their daily professional lives. The issue came up really from a region, and they said really what we need is a 90.1 app. It's kind of like your tax, fill in your tax form. Now it's much more complex than the tax system, believe it or not. Would wonder how that could possibly be. But we are working with some organizations where we can do some sort of transitions of apps that will work with other software that will make it easier for people to use the assessments for 90.1 and other standards. We want to develop a portfolio of programs and courses that chapters can offer their members. We feel that the programs that we have today are not that easily applied at the chapter level. There's actually an ad hoc committee that's just been created with 3 members from Pub Ed Council, 3 members from Membership Council, and they're going to be working on finding out what the chapters could use, would use, the format, the materials, and we're going to start working on these materials and packaging these materials for use by the chapters. So the entire strategic plan is on the website. So if you go to ASHRAE.org, strategic plan, you can read the entire plan, and there'll be updates to where we are with the various initiatives throughout the year. So Members Council, that's not a council that I chair, but it's the one that really represents the grassroots of our society. So so they're reviewing the flexibility and commercialization policies to assist chapters in formation and support. They're trying to get the right sort of mixture of commercialization policies. Reviewing ASHRAE marketing to ask on behalf of the members what's in it for me question as a membership value proposition. So there'll be some surveys coming out in the future to say we're trying to understand what's in it for the chapter members. Developing more cost-effective ways to deliver products to the chapters. That's the overlap between Members Council and Pub Ed Council about products and materials. And reviewing the structure of CRCs to ensure they continue to meet chapter and regional needs. One of the things that's been a challenge to many CRCs is centralized training. In some ways, centralized training is good. It seems to have made a difference, particularly in the area of research promotion. But in other ways, it actually starts to take people away from the CRCs. And the CRCs are that regional team development opportunity. So they're studying that, the whole approach to centralized training to see where we should be going with it or not going with it. Pub Ed Council, again, this is the area that I'm involved with directly. We're developing programs for building facility owners and operators to support and enhance the effective operation of building HVAC/R systems through education as well as evaluation of operational tools. It's an area that we have not been strong in any time that I've been involved with ASHRAE, but we do have to find a way to connect with those building owners and operators and say, how do we all work together to make a better operating built environment? And so we have an ad hoc group that's getting together. We're going to bring in people like BOMA, IFMA, the higher education facilities officers. We're going to bring them into a meeting and start developing a strategy to move in the right direction on this. We're going to determine the appropriate products and tools to be developed by ASHRAE to enhance the residential built environment. As you might be aware, we've decided that we're not just going to watch the residential built environment anymore. We're going to actually get engaged with it. Actively, we had an ad hoc committee that said, evaluated this situation and said that we really do have something of value to add to the residential market. And so as the the tool, as the information develops about products and materials, then PubEd Council will respond by working to develop them and disseminate them. And then we're going to develop a development package, practical application programs for delivery through the chapters. Again, I said that's that overlap with members council. We have ASHRAE Exchange, which we played a little bit around with LinkedIn and with Facebook and decided that we should create an exchange methodology that we could have members exchange information on ideas and ask questions and have other members answer it. And so that's up and running, ashraeexchange.org. So if you want to get on there and start a discussion about a particular application or a problem or an issue, that's a good place to go. We have a lot of new seminars under the ASHRAE Learning Institute. Complying with Standard 90.1 2013. Significant changes to 90.1 2010, IECC 2012. And a bunch of new short courses. So we're always in the process of producing and enhancing our courses. And they're well worth considering being part of. Under the Institute, we also have e-learning, online learning. And we've been doing a lot of work on the website. It's much easier to navigate on the website. So if you struggle with e-learning, you might want to go on and have another look at it and see if there's any programs that would be of use to you. We have the new courses, Standard 189.1, Humidity Control and Building Information Modeling. And finally, in these programs and courses, one of the big successful programs is HVAC Design Training. Now that's instructor-led. As much as you hear about online and web-based courses, the instructor-led ones are very popular. Joel Primo is part of this program. And there's level 1, 2 that we do it. We've had a lot of attendance, and we've done them in New York, Dallas, Toronto, and Dubai. And most of them are actually held in Atlanta, though. So it's actually not a bad place to go. Sometimes it gets icy down there, so maybe not in the dead of winter. Anyway, they've been very popular and great feedback on them. So if you have a chance to go, it would well be worth it. The other thing we have all our advanced energy design guides into our quality guides. These are all free. You can go online and download these guides, and if they're of any use to you, that's well worth going online, spending a few minutes, download them. They're free. And the reason why they're free is that the federal government in the United States contributed a serious amount of money to this on the basis that once they were developed, they would be free to the public. So it's all part of our work of trying to improve things and use government funding whenever possible. We also have an ASHRAE Code Interaction Group, and they work actively engaged in development maintenance of over 150 standards. The value of standards realized when they are adopted and used, particularly in codes. So quite a bit is done in code language. And the Code Interaction Group works with other model code standards writing organizations to adopt their codes. And one of the major initiatives under this was actually getting the 189.1 as an ICG code. So when that's finalized, 189.1 won't exist on its own in North America. It'll be an ICG code. And that's how you will actually purchase the standard. It'll be through that process. But it'll be joint. I think actually there's a slide on this. There's a joint program between ASHRAE, ICG, and the lead organization to enhance and make it standard language in code language. And finally, if you have the desire to have a chapter scholarship, it's a $60,000 target total. Regular scholarships are $100,000, but for the chapters, we set a goal of $60,000. And I believe the rules have been changed so you can build it up over 5 years now. I don't know if somebody, I'm not on that scholarship group anymore, but you can actually contribute over 5 years to get it to 60. And then the society will manage it, manage the money and write the checks every year for your scholarship, done in whatever fashion it is that you want it to be selected. finally, maybe not finally, BEQ. It's a premier program that we're working on. We actually have, it's been extended, free submissions offered to qualified ASHRAE members. And I don't know exactly when it's over. I think it's over in March. It was supposed to be over in November, but we extended it. And it's really to actually do a building energy quotient, basically a label for existing buildings. And actually we've done 2 buildings so far on our campus. If you have when we used the building energy quotient label from last year, and we did a residence, it was very easy. We did a multi-use building, and it was more difficult, and they made some changes, so we're going to rerun it. But it actually gives you a good sense of how your building is doing in comparison to other buildings of similar type. So it'll be a good program, but it needs more data, it needs more people working with it. Oh, here's the streamlining building. This is where we're talking about moving it into the ICG and working with LEED. So I've done that already. ASHRAE in the house, I've done that as well. This has come out of that the residential ad hoc. And High Performance Building magazine website has been worked on. We believe it's been greatly improved. We've done a lot of work on websites. Revised website features new design and fast and accurate site search. Fully responsive on mobile devices, content organized by topics such as envelope, light, and site. So it's well worth going to have a look at that as well. I think you'll be impressed. And we have a bunch of new publications out. Load calculation, chilled beam, geothermal, data center, standard 189, standard for design high performance green buildings is out. Now if you want to buy 189, you have to buy it quick or it'll be the ICG code language. Science and technology for the built environment. ASHRAE's research journal, anyway, it was called HVAC&R Research Journal. And we decided we'd have a review of whether that really represented the content, and decided that it's really a science and technology for the built environment research journal, so it's been renamed, and these journals will be coming out under that new title the next version of it. And if you want to join us for some things, there's the April 23rd webcast, new tomorrows for today's buildings, existing building commissioner. May 22nd, 24th, International Conference on Energy and Environment and Ships, if anybody's working in the ship industry. And June 27th, July 1 is our annual conference in sunny Atlanta, Georgia. And then September 30th, October 2nd, Energy Modeling Conference, Tools for Designing High Performance Buildings in Atlanta, Georgia. And then finally, if you want to go to Mexico in October, the AHR Expo in Mexico. So that's pretty much a wrap up on what's going on at Society for the year, and particularly from the winter meeting. So if there's anybody that's not eating that has any questions, I'll do my best to answer them. If not, we'll just all eat.
Anyone?
Thanks, Darryl. And more of a local point to one of the items that Darryl brought up. For the last few years, we've been considering creating an ASHRAE Ottawa-Valley chapter scholarship. So originally the requirements were $60,000 over 3 years, and we had petitioned to get that increased. So hopefully, Darryl's surmising that an extended would help us. But that is in the works for Ottawa-Valley chapter. Part of our research promotion goals, and more information on that will follow, but consider that as you make your RP donations. So enjoy the rest of your meal, and we'll get to the evening program shortly. Servers finished clearing away your entree. There's one more item of business that we need to take care of. I'll make the draw for the Sens tickets, so if you all want to pull your draw tickets out. Chris Fudge tells me he's got the winning one. Actually, I'll get mine out here first. So all right, here we go. Bob, go back. Pick a one. No. And you could win. Actually, no, you can't. You can't pick your own. Oh, yeah, all right. The winning ticket is 793722. 3722.
Close, 2-6.
Excellent. Excellent. Michael Grant from Train is the winner. There's the tickets. And let this be a lesson to you all that karma pays off. Recent volunteer for ASHRAE to help out with our CTTC promotion. You win sends tickets. So there you go. Life looks after itself. We were successful in raising $390 tonight on that draw, so that's excellent. It goes rightfully towards ASHRAE Regional's promotion. Thanks again to George for doing all the legwork. So there is coffee at the back. Feel free to help yourself. We're actually pretty full tonight. Normally I ask the people on the sides if they want a better seat to come to the back with open seats on the table, but if you want a better view, you don't have one, just bring your chair to the back and take a look. And with that, I will introduce Daryl Boyce. Daryl is currently the Director of the Department of Physical Plant Services at Carleton University. Is the Assistant Vice President, Facilities Management and Planning. Like I mentioned before, Daryl has been an ASHRAE member locally at SSI level for a very, very long time in a variety of roles. And the Ottawa-Valley chapter has been quite successful in moving people up the ladder into regional and societal roles, and I think Daryl has exceeded our expectations in that front, so we're very lucky to have him here as a member of our chapter and to be able to give the presentation tonight and also information on ASHRAE Society like he did earlier. So without further ado, ladies and gentlemen, Daryl Boyce.
So I think a number of years ago I said I really need to present on the SNOLAB, this wonderful scientific journey that I was pleased to be a part of. And so it's one of these things where you say, you've got all this information, and you say, well, just schedule something and I'll do a presentation. I don't know who it is that's really nervous. There's somebody who's been calling me regularly or emailing me regularly to say, you got that ready yet? And I say, oh, no, the weekend. So anyway, I did actually get around to doing this, and hopefully it'll be of interest to people. There's a lot of pictures, and the reason why there's a lot of pictures is that it's really an experience to really understand the mine and the building of a structure and a facility within a mine environment. It was a very exciting project, and we'll begin the journey with a few slides right now. Maybe not. Well, let's start again. There we go. And it's really about going underground to understand the universe. And it's the creation of the SNOLAB, which was an extension of the Sudbury Neutrino detector. So I'm going to talk a little bit about the Sudbury Neutrino detector, the sort of phase one of this grand scientific journey. Then the SNOLAB project, I'll talk a little bit about the surface facility that we had to build and why we had to build that. I'll go into the underground laboratories, what it took to build facilities underground, the challenges, some of the solutions, and just give you a glimpse into some of the research that's being set up and undertaken at this time. So there was a university consortium, and it was led by Queen's University. Carleton was part of it, Laurentian as well. University of Montreal and UBC, and that was a group that built the snow detector, the first phase that I talked about. And it was to explore the nature of neutrinos, almost massless elements that are going through us right now. They're generated, a large number of them are generated by our sun, and other suns generate them as well. It's part of a nuclear reaction with the sun, from the sun. And they need a lab with a significant depth to screen out the background radiation, because you can't pick up any interaction with these small, very small particles with all the background radiation that we have on Earth. And they created a detector facility 6,800 feet below ground, 2 kilometers below ground. So the first phase of the facility was constructed, and the estimate, I'll talk a little bit about how this was done. The primary researcher for the first phase was out of Queen's University, a very well-known particle physicist, a very, very great research person in particle physics. And when they got the money, the university said, okay, go ahead and build your thing. So they got $30 million, and when they're done, it cost $100 million. So this was a researcher doing a research project underground, and it really was research, and what the dollar value was whatever it was, right? So the detector, as I said, was constructed 6,800 feet below ground and occupied 11,000 square feet with a cavern for the detector, a control room, and a utility drift and a service drift. So not much other than a detector and small service space around it. So it was built by creating a large cavity, picture 9 floors of space, hole that deep, 9 floors, 60 feet wide, 60 feet in diameter. Then the cavity was sealed with a membrane because the detector itself had to be protected by a water barrier around it, ultra clean water. A 12-meter acrylic vessel was built in which the detector fluid was placed. And as I said, the space between the vessel and the wall was ultra clean water. And the researchers actually had to design and build the equipment that cleaned this water and took all the air out, because if you left the air in, there was particles within the air that had radioactive material, and that would mess up the readings for the detector. What they did is they manufactured this vessel underground. You can't bring it down a mine shaft in that size, so there were 2-inch thick acrylic panels that were welded, glued together to create this watertight acrylic vessel. And it was filled with 1,000 tons of heavy water. So this all came from Atomic Energy Canada, and the value of that heavy water that was in that vessel was $350 million. And they had to get back every ounce of it. I mean, every ounce. So you had to know how much went in, how much went out, and give it all back, or you had to pay that 350, so whatever you left versus the cost per ounce. And the vessel was then surrounded by an array of 10,000 powerful photo detectors. Just to give you a bit of scale on where this is, just in case you haven't figured it out yet, there's the site of the lab. That's the CN Tower, and this is where you are down. And all this yellow stuff is actual mining area for nickel. They get probably enough gold out of that also to fund a good part of the operation, but this is the vein of nickel that is being mined in the mine. Now, this is a view of the entire site underground. This is the original detector, and this is the basic facility that was built with ancillary space built to support the operation of this underground facility. So when we got up there, when I started this thing in 2005, this was the building that supported the activities underground at that time. And there was a bunch of site trailers in the back that was the offices for all these top researchers to come and stay when they're on the surface there working underground. And so the very first thing we did was build in this building. So it's about a 30,000 square foot building on the site, and this is actually on a piece of land that's leased to the Snow Group by the mining organization that was Inco at the time. So it's actually on the mine site. And then it's really made up of research areas where they can prepare the research equipment to go underground, and they get it all put together, assembled or taken apart, put into containers, airtight, sealed, clean containers. And they go on rail cars, go on the railroad line, you go in and go down an elevator. And that's how they get all their materials underground in a sealed container. To go underground, this is how you look. So you dress like a miner, because you are in the mining world until you get inside the lab, which is a clean lab. And this is your luxury elevator. They call it the cage because it's just a metal box, and it's a double-decker cage too. So what you see here is there's another deck above it, or below it in this case, and you get on there with the miners or with the research group, depending on which time frame you're going down, and go down that 6,800 feet. And you get to the bottom in this particular drift, and you find out it is the home of the Sudbury Neutrino Observatory. And so there's a sign there that says that you found at least the right level in the mine. And it gives you a sense of what you have to walk down. So this is actually the elevator down here, and then there's rails that go all the way down the drift to the actual site of the lab. So you're just walking down this muddy, wet drift, 1.8 kilometers to get to the research lab. And then you take that journey, you get down there into the original unit. You used to come up on it right in here, and this was the entry point for the original detector space. This is a picture of the original refuge area. What's of interest, and you should remember this surface here, you see how it all looks very rough. That's shotcrete, and it's just regular shotcrete, and then they painted it. Remember now, this is a clean lab, so imagine how much paint would have to go on that rough shotcrete to actually get it to a point of being a clean lab. So it was not a very good idea not to do something with this surface. And they had equipment everywhere because they had no space, so this is one of the corridors down that service area. And then this is the high-quality air handling system they had in place. Your basic galvanized steel, very noisy. You could hardly even talk in that area because of all the noise from the air handling unit, the exhaust fans, etc. And this is really showing the ductwork in that. We're trying to create a laminar flow environment for a clean lab, and this is what they actually built. So here's an artist rendering of the detector. So you have the acrylic ball. You had this array of photocells around it. The cavity was filled with the ultra-clean water, and then they were looking for neutrinos to come in and hit something and give off energy. That's how they were going to actually determine that there was this particle that gave off energy. It's a picture from inside the cavity before they closed it up, and it gives you a sense of the size of the acrylic vessel and all the photocells that are on it. So that's what's inside this 9-story, 60-foot diameter chamber. So if there's a problem with a cable or a photocell, they have these little submarines that go down. They can actually go down and maneuver and maybe bump into something and put it back into where it belongs. So they have those to go down and check on things. But if they have a real repair, they send a man down. And so it's big enough for a man to go down in that chamber into the acrylic vessel. Not something I wanted to do, nor did I do it. And when we're talking about the photocells, this gives you a sense of what they look like. These are all turned around the right way. This one is just turned around that way so they can get a sense of how well they're working. So, that was the existing lab, and now I'm going to talk a little bit about the expansion. So really our challenges were constructing a building inside a mine. I think that anybody would see that as a challenge. The other thing was the rock temperature is 42 degrees C, so it's like being in a 42 degrees C constant climate year-round. Facility needed to be a clean lab, and it's operating right now at class 1000 inside a dirty mine where they blast and remove ore. The delivery of materials is challenging because I showed you the elevator, the cage. You could actually hang things off the bottom of the cage, but they didn't like to do that because if they banged around and everything, they could wreck up the rails. but they would do it on the odd occasion. We need to continue the operation of the snow detector. We couldn't just stop. So we had to work around that to a certain degree. And they had to operate the facility in active mine. And the 30 million to 100 million, this budget was fixed. The government, which funded the 100 million, our government, called the federal government, figured out that maybe they shouldn't leave it open in their contracts anymore, so they closed it. And they said, you're going to get $49 million, Carleton University, and you're going to build what you say you're going to build, and you get no more money for this. And if you can't build it for that much money, you find the money. And so that was another challenge that we had. Kind of a usual challenge for me, but for the researchers it was a little bit scary. So this is really the part of the facility that we built, just getting back to that model. So we had these drifts, as they're called, and then we had a cube hall and a cylindrical hall. And a new spot for the ventilation system to come in and the materials come in and through a clean environment. But to start construction, you had to blast, right? It's kind of the opposite of building a building. You have to actually blast out the space. And so they come in, they mark it all up, they drill the holes, put the blasting material in, blast it, and then come in and muck it out. This actually isn't a bad picture of why this is the right place to do it. This is really basically fundamentally solid granite and solid rock, and that's why it provides the shielding that they needed to actually get rid of all that background radiation to allow them to do this very finite research. So once we do the blasting, and then we had to actually come in and bolt back the rock and put wire mesh on it. So we have something to put that shotcrete onto to start forming the walls. And so they come in and they do the wire mesh and bolt back the rock. And what they would turn out to develop is a drift that had a rough finish with a rough floor that we would then finish up. I'll show you a little later on how we went about that. And then some of these drifts would come into the top of one of those halls. In the case this comes up into the cylinder hall. You can see the men in here looking over the safety rail, and they're looking down at the excavation equipment in the bottom of the cylinder that's mucking out the debris from the blast, from the previous blast. So that's how they mucked it out, the cryo pit. And that's a view from when you're down there with the equipment. You climb down the ladder down the side, and you get to the bottom, and you can see how high up it is. So again, it's 50 feet cylinder diameter, 50 feet high to the bottom of the crown. Now to excavate it, they actually come in at the top, and you excavate the top, and then you go to the bottom, you excavate a drift down to the bottom, you go underneath to a certain degree into the space you want to excavate out, and then you drill a hole down, and then as you blast the stuff from the top, you muck it down the hole, and so it would go down through this hole, come out on the other side, and then it's taken away from the other side here. So just all the debris from that large cavity would shut down the hole and out the bottom. In our case, it would go to a crusher, and we crush it, and then we sell it back to the mine for road bed. So they always needed a smooth road bed to run all their vehicles around the mine operation. So we paid to crush it and sell it back to them. And that's our way of not having to move the rock up to the surface, because that's very expensive. The other part of it is that we need air. You can't operate a building or a facility without air. So we actually had to drill another air shaft. And what you see here is actually the drilling coring machine that's going to do it, or the head of it. And this is the machine in place that to draw that head. So you put down you drill a small hole down, you put the shaft down, and then you pull the head up towards the machine. So you've got that compression that's helping you break the rock away, and the rock falls down at the bottom and gets removed. So that was the coring machine that ended up giving us a vent shaft like this. So we could have our ventilated air coming from the other vent shafts down to the area that we wanted. Now, to actually continue this development of this space, we actually had to build shops to repair equipment. And this piece of equipment actually I bought as part of the project because we needed one of this size to muck out the excavations. So I actually bought that piece of equipment. Later on, we just dismantled it and shoved it down some hole somewhere in the mine. So when you're building it, this is actually the new area where the rail line comes into the lab. And what I wanted to show you here is during the construction we had this ventilation air through this yellow sort of fabric ductwork. And then the final ventilation air for the lab would be this spiral duct that we built into the air handling unit. And the fresh air handling unit we put up on a platform above that materials arrival point. When you come into the building, you come through an actual man entry into the lab, and that's basically this narrow space that takes you along. On the other side of the wall is where the materials come in the car wash, so they actually clean the car and take the materials out from a clean environment into the clean lab. And so this is the other side that has the rails running into it, and the actual materials are taken out of these rail cars that come down with the materials for the lab. Now, remember that surface I showed you before of the old facility and how rough it was? This gives you a sense. This is a finished shotcrete in our side of the facility, so it's much smoother. It could probably be properly sealed, and then it's kept clean much easier than that rough material. The rough material, dust kept coming out of the little cracks and pores all the time. I talked a little bit about the rectangular hall, and here's a view of the rectangular hall when it was just being finished. You can see the smooth shotcrete that's on the sides here now. It's been smoothed up, and we have this major stair that gets you from the top to the bottom, or the bottom to the top, for research purposes. And to do that smooth shotcrete, they actually brought a machine down underground that actually mixed it, blended it into that more malleable material. And these guys spent months troweling walls. They take that material, it's just like a plaster, and they trowel every inch of those drifts in the grand halls, the rectangular halls, the cylindrical hull. These guys, when they're not doing this, they're troweling the materials on these bobsled runs out of a company out of Quebec. So once you get the smooth surface, you've got to actually seal it, so you get a sense of the unfinished and the finished here. So we actually had research people painted all this with, as you can see, with a roller. And you can see when you blast it out, it isn't always smooth. There'll be rocks that stick out and material that sticks out. You just sort of cover it up and paint around it. So you won't get that smooth wall surface because it's just not the way the rock behaves. And for that same cylinder up above, we had this area here where you can run materials in and load them and drop them down to get access at the upper level, and also provide access to that stairwell that gets you down to the personnel. Another challenging part of this was putting all the ductwork in that you had to get into the space that you're in for research. So it was quite an art form to get the ductwork all put into place. We actually brought a spiral machine underground because it's a flat material under than it is preformed ductwork. So all the ductwork underground was actually manufactured underground and then installed. I must say that the sheet metal organization that did this did just a bang-up job. They really cared about their work. One of the things we did do during the construction, and this again is the researchers, you've got a bunch of, I suppose they're not all that busy because they don't have the research up and running. So they actually did these models in their research modeling about how we would put the ductwork in and how these railing systems would work to support all the cable trays and etc. And so we had a methodology where we'd have basically boxes with diffusers and then low returns on on the research space to get that more laminar flow, bring it down and take it out. And so they did a number of these models, and they modeled it actually, they changed the model when they understood the actual where the rock was. They remodeled it with the variations of the ceilings to make sure we get all the ductwork in and they still have the space they needed for research. We modeled the air handling units that had to be actually in the research space with the people to see how that would all work. And now we're seeing a little bit more of the finished product. Again, we're up the air handling unit. These are the boxes the materials come in that are sealed up airtight to keep the dirt and dust off the research equipment. And this is a nice service ladder up to the air handling unit. And there's 7 filtration areas in the unit. There's sort of a pre-filter, HEPA filter, 2 charcoal filters, 2 pure fill filters. Because we have to get not only the particles out, but the gases from the mine operations and blasting. Again, it was a bit of an art to fit all this equipment in. As you can see, we have rock here, and we had to, you build it, and then you put the air handling unit in, and you say, gosh, we just got that one in. Those types of things happen. At this entry level, we had, really gives you a sense, here's the fresh air supply. And then this is the general exhaust from the various areas. So any of the contaminated exhaust, we ran a duct right out to the exhaust shaft. But the general exhaust, we just exhausted back in the drift and let it go down the drift with the rest of the sort of mine exhaust air. But the fresh air vent ran away down the drift quite a ways till it got to a spot where it was close to the fresh air delivery point from that shaft that we cut through the rock. And then this is a sense of fitting it up with these structures here that allowed us to put all the cable trays and deal with the sort of unevenness of the walls, right? We could adjust it by having this. And all through this, we're trying to figure out what do we do to, all the way through it, we're trying to figure out what material do we use to hang all this. And we just sort of kept saying, well, we try this, we try that. We did a couple of pilots. We did the 3-dimensional views of it, and then ended up with some products that I think are pretty good. Air handling units had to have pads, and built those into the concrete floors. And this is a picture of the finished 50 by 50 cube hall with all the researchers at the bottom. To give you a sense of the height of this. So it's quite a deal. It's all painted up and ready to be ready for the research components to start being installed. And then that's the rail that they can lift things down with. If you remember back when I said here's the entry to the old facility, well, this is the entry before we made it into Clean Lab. So we had to come in and rework all the lines, redo the walls, reseal them, put the floor in. And we had to take that, what was outside into the mine and make it inside. It's probably the hardest part we did. One of the interesting things, or problems about a facility like this is you have people down there and there's washrooms down there and there's effluent from the washrooms. And this was their system to get that sewage out of the lab. So they pumped the sewage into this vessel here. When it was full, they would take it to the elevator and they'd run it up to the surface. So you're 2 kilometers underground, so it's under quite a bit of pressure when it's down there. And as you're going up in the elevator, the air pressure gets less. So the gases and smells from this thing don't stay inside the vessel. And so it's not a very pleasant ride. And they hated it. And they said, Daryl, if we build this thing, you've got to put a sewage treatment plant in here or something. So we did. And here it is. So this unit here handles all the sewage from the plant. It's pumped over this unit. And it treats it. It eats a lot of dog food too, by the way. So it needs a lot of biomass to actually function. But it functions really well. And what comes out of it is basically gray water. And the gray water is something that you can just pump out of the mine with all the other water that comes with the mine. So it goes into a mine drain. It's pumped up with the rest of the non-contaminated water, so to speak. So now we're starting to see the fit up air handling units in place. You can see some of the areas are a bit narrow, but it's okay. And we're just starting to dismantle the ventilation air for construction. We're starting to move the construction people out. Now this, I know this is, it's not really an advertisement, but it's, what we had to do is find an air handling unit or air handling unit types that could live with the people and not drive them crazy. And so we put out the standards to market and ended up buying, I don't know if people know it, but this is manufactured just north of Montreal. And powder coated exterior, so it's nice, it looks nice. It looks as nice as the wall finishes. And you cannot tell, you can tell by the magnet here that this thing is running, but you can stand beside it, and you don't know it's running. It is that quiet. And I'll tell you, they are so thankful that we didn't put another one of those noisy units in. They're just wonderful. And then I showed you how we were putting the ductwork in, but this is kind of the finished ductwork in here. You can see we had to elevate a couple of the air handling units up in the air to serve all the areas. And then this gives you a sense of the finished floor and everything in those clean labs just before they're being turned over to the researchers. I mentioned before about the ductwork, you know, this ductwork with diffusers running down the middle, and then we had those returns. We thought we were designing that way. Well, I went to an ASHRAE show, and I'm walking around and I see this fabric duct, and I walked over to the guy and I said, oh, that'd be interesting. I said, you do this in clean labs? He said, oh yeah, we do lots of clean lab stuff. And I said, well, let me go talk to my researchers. I think this would work. And so I went and talked to research, and they said, oh, we don't know. We think we should probably have rigid duct. And I said, well, let's give it a try. So they said, send us some materials, we'll test. And we had to test every material that went in there to see if it had bad properties for the research. And they found a material they liked, so we bought it. And the thing about the rigid ductwork, when they put the rigid ductwork in, when you put it in, and then you go to clean lab, they actually had people go inside it and clean it with toothbrushes. That's how much cleanliness they did. All those cable trays were cleaned with toothbrushes to get all the dirt and all that radioactive carrying dirt. So this, they put it in, they ventilated the space while they're fitting up some things. They wanted to go to clean lab, they take it all down, they ship it up to the surface, they wash it, bring it back, bang, it's done. They think it's a miracle drug. And the other thing we had a grand problem with is how do we ventilate that cupole? And all we had to do was use this fabric that ran it across the top, down the side, and like this. And it's like you don't hear any air noise, and the space is just cool. It's just an amazing application for that particular product here. It was one of the big ahas at an ASHRAE show. And again, that's the air handling unit with finished up. And I'm going to comment on this because why not? Lighting guys, they overlight everything. You could tan yourself down. And I said, you got too many lights. They said, oh no. There's, they get old, you don't maintain them, they burn out, you know, all this stuff. And so we got to put all that light in so you'll have light when you don't maintain it. I said, this is a clean lab, we're going to maintain these things. I gave up. This is one of these idiosyncrasies of the mine. Low voltage, but yet they insisted that we had this kind of armored conduit, flexible conduit. So what goes into it? So first of all, in an underground lab like this, 42-degree rock temperature, all you're ever doing is cool. You never heat because it's naturally heated. And so you have to understand the energy balance. So we put our scientist guys to work again, and they did this wonderful energy balance where they looked at all the various loads and added them all up and to try to understand the amount of chillers we needed and the amount of diversity we needed. Then they did a spreadsheet. I know it's not really readable, but interesting thing about this spreadsheet is the almost 24% of demand is from the rock load, the temperature of the rock, looking at cooling down to get that to the temperature. And another 30% of the load is from the mine air that you get, that so-called heat. Fresh air is hot fresh air, so you got to cool that. So a lot of what you're doing is just dealing with the fact that you're underground. terms of the cooling. It's a bigger part than the actual equipment personnel. So we installed a chiller plant, cooling plant, which is basically a bank of chillers. And then to do the exchange, get rid of the heat off the chillers, we actually put in air handling units. And so what happens is that the ventilation air that comes through the lab and everything, then goes up and exhausted to the surface, flows through these and actually exchanges and picks up that heat off the chillers and takes it up to the surface. It's the only way we could actually keep the chillers operational. And we chose to put in 5 90-ton chillers. So that allows you to sort of, in the early days of the research, you can have just a small number of the chillers working. We figured the maximum would be 4 chillers, so you always have one in reserve in the event that one of them breaks down. And these came out of a supplier out of Toronto, actually. So that's the cooling side. The next side is actually the ventilation requirements, understanding them. So you've got a lab, and we figured out that we had 5,000 CFM, and so that we would bring that in and we have to ventilate, put proper air and everything. We looked at our losses through the doors and through the car wash and through the regular exhaust, and calculated the whole ventilation system. We do have an operational challenge that not every building has, is that the mine is still active, so they blast. And this ventilation duct that I talked about ran down the drift actually is closer to the blasting than the lab is. So when we're using ventilation air and there's a blast going on, we know, they tell us when it's going to happen. We actually shut off that damper there, and we just take air locally, just so that we don't bring in those blast gases, the CO and the other gases come off. And then under normal circumstances, when we have good mine air, this is open and this is closed, and we'll bring it in. So it's kind of this way of operating, keeping the facility under positive pressure, keeping it as a clean lab while all these blasting events are happening. They weren't supposed to be mining near us, and then they decided to go back and clean up an area. And they started blasting and blew one set of our doors right off. Just blew them right off. It was an area that we hadn't fit up yet, so it wasn't too bad, but it's necessary evil. Now, controls. If I talked about the original lab, that was really mostly pneumatics on the air handling unit, and then they had some PLCs, sort of industrial grade PLCs, more for monitoring. And they had noisy air handling units, I mentioned that. So these are things that we should stay away from, and they had some pretty ugly wiring situations. So in the new SNOLAB, we wanted to implement cost-effective universal design of the controls. We wanted to plan for long-term operation and migration to maybe newer control products easily, account for the unique application, replace unnecessary pneumatic controls. Any of the pneumatics that were there that we could get rid of, we would. We wanted to improve the comfort and improve the ease of maintenance of these controls underground. Challenges were mine installation standards. So you're in a mine under the mine rules. But when you step inside the facility, you're under a facility under industrial rules. So just like a research building and an institution. So we convinced the mine that once we get inside the building, we can use building standard tools except for those conduits. But the other thing is blasting in the mine. We had to worry about that. We'll talk a little bit about that. Counterintuitive programming, equipment size, and high amount of network activity. So the research has a fiber that runs from underground 6,800 feet up to the surface and over to the building. And we wanted to put the network, the building automation system, on that same fiber. So we had to worry a little bit about the amount of stuff on it. So again, with the blasting in the research labs, we had to actually design them so that they could accommodate the pressures from the blast. So a research lab may normally need 540 CFM for ventilation purposes, but we wanted to have available 2,000 CFM to add into there when there's this air wave that comes at the facility from the blast. And so we had basically 2 valves one to run the normal 640 and the other one to boost it up to 2,000 in the event of a blast. And then when we get to the areas, the sort of individual lab areas, that's each air handling unit serves a particular lab area. We had to actually supply air to the labs, return air from the labs, and then since we're always only cooling, we could have a cooling coil with a bypass so that if it got a little too cold in that lab, we'd just bring recirculated air, which is warmer in, and blend it. And filtration was also required of these. And of course, as I said, the 540 and the emergency overrides for pressure. And so this gives you a better look at the individual air handling unit. So we wanted to have standardized controllers with Ethernet backbone, zone control implementation to be ongoing, fiber link to the surface I talked about, operation and maintenance largely controlled above the ground so that the regular operations of the facility were controlled from that building up on the surface. We had to have high resolution monitoring of the mine gases, and we had to maintain this class 1000 clean room. So we had to measure pressure, temperature, humidity, gas levels, H2S, NO2, CO, and CO2. So we had special sensors in specific locations to do that. We had to monitor equipment performance, electrical energy usage, and had to alarm to the surface in critical applications. So basically, we installed a building automation system. Matter of fact, it's the product that we use on our campus. We actually care and attention with the wiring, so it's much nicer, much more properly labeled, and much simpler. And you just need a PC for the monitoring in the mine below. This one's actually underground, and then there's a much larger monitor up in the control room. And so we got a system that was state of the art, finished within budget. And I'll tell you why the budget thing was interesting. When we first started the design of this, we had a company that does a lot of work designing facilities for the mining industry. And their estimate on the building automation system was $2 million for this 30,000 square foot building. And I said, oh no, we're going to use regular building controls. So we got it down, even with the specialized nature, to about $300,000 to $400,000 for the entire building controls underground. And we've trained the scientists. They can maintain most of the features of it. You know, they call when they get into trouble. And it meets the needs of a unique application. The other interesting thing is that we had to build them a kitchen area. So the only way up and down is that one elevator. And when that elevator goes out of service, you're down until that elevator is repaired again. If there's an event in the mine, and they let out a stench gas to warn you that there's an event, you go in here and you stay there. You don't go out of that room. So they had to have facilities to keep them healthy and sane during these events. Now we're starting to fit it up. So you can start to see here the research equipment's going in. Clean lab, now you start to see people dressed up in clean lab. So you get there, you take off your mining gear, you shower, leave all that dirty stuff behind, you go in, you put on this clean boots, clean coverall things, and a new hard hat, clean hard hat, and you're set up to work inside the lab. Now this one here, it's a little bit hard to read, but this is dark matter with a research program called Picasso. And will they be creative with their names? But it's all about trying to understand dark matter in the universe, which seems to be a theme of what they're doing. This is another fit-up area of this research area. You can see the amount of equipment that's starting to come in here. It's hard to believe, but that's a minor part of the load. You can start seeing how that cube hall is getting fit up with a platform in here. And what's going to go into that is this device here, which is another research piece of equipment to study dark matter in the universe. So there's definitely a theme around dark matter. And all the time, the research is still going on in the detector. As I said, it's got a new scintillator, this lighter than water soap-like material fluid, and they're still trying to, they've actually focused now on stars other than our sun, trying to understand neutrinos from other stars. So it's quite an interesting project. It's been a wonderful experience for me, opportunity of a lifetime to be responsible for building this and managing the expectations of the research community, yet giving them what they say today is an excellent facility to support them well into the future. So with that, I'll try to answer any questions about dark matter. Yes.
How did you bring the major mechanical equipment down, especially the chiller? Right-hander, you usually can ship them in modules, but
So the chillers were actually small enough to get into the cage as well. Yeah.
vertical, like hanging?
Each one. No, they fit inside.
Oh,
If I
What's
could
the size of
actually,
the cage, Daryl?
it's about 8 feet across, and then it's got a height of about 12, 14 feet. And the length would be about 14 feet as well. So it's not bad size. You can't bring a whole air handling unit down. And what was important too about our specification was these air handling units had to be in modules that would fit into the cage, because we're not hanging. The things that we hung from the cage were real steel members that had to come down, and we didn't want to weld them again. But even then, sometimes we cut them out. It was just easier. Even the equipment, I showed you that big piece of equipment, that's cut up to bring down. And they re-weld it when it gets down. That's why we buried it down there, because it cost too much to take it back up. Yes?
I'm curious, how long did it take to take a trip down?
Oh, it depends how many miners they let off and pick up, right? It's if you go down, it's like 5 minutes to go down if it's express, or it could be 20 minutes if they stop at many levels. And it depends who's driving it too. Yes.
At the beginning of this wonderful speech, you talked about heavy water. I'm a little bit confused about that. You said that they used a large amount of heavy water and they had to get it all back. What was that all about? What was that all about? What was it for?
Well, heavy water is the material used in nuclear reactors, and so this and it's very expensive to create it, as I understand it. I don't do that, and so Atomic Energy Canada had this amount of it that had been created for use in the next reactor that they sold, right? But they weren't selling any reactors, and so what they did is they just leased it from them. But they had to have an insurance policy of $350 million on the water. So if there was a leak, a major leak, and that water disappeared, they would have to pay Atomic Energy Canada $350 million. And it was a critical aspect to them being able to see this small release of energy when this minute particle hits something and released energy. And I don't understand the science behind that either.
Okay, so the heavy water is down there and it remains down.
It's gone now. So they took it all back. They're stainless steel tanks, and they took it all out. They measured every little bit of it, and they took it all back. And I think they lost a little bit of it, but it's...
So they used the heavy water for part of the science, part of the experiment. That was done, and then they took it all back.
Right, yeah, because we didn't want to pay $350 million for it. And what the science that they did when they had the heavy water, so in 1958, 59, there was a scientist in the United States that had some reaction. He had a tank of some fluid, and he was underground a ways, and there was a reaction. He says, I think there's a reaction here. There's a particle that's very small. I'm going to call it a neutrino. So he postulated that the particle existed. This lab, with this research, using the heavy water, validated his postulation, and he got a Nobel Prize in Physics. He got the prize in physics, and this lab proved that he was right. And that happened in 1998. Yes?
What year, Daryl, was it that you built this?
Well, we started in 2006. We're substantially done in 2010.
I was going to ask, is Carleton the only user of the facility, or is it leased out, so to speak, to other organizations?
No, it's a consortium, and you know, it's an interesting situation. So we built it, and we built the surface buildings, so technically we kind of own them, but it's the consortium that owned it, this SNOLAB group. There's a group, and it's like the original group, Queens, Carleton, University of Montreal. UBC, I don't think's in it anymore because they have their own problems with their high-tech research. And then what they're doing is that researchers around the world bid on time and space under there to do their research. So it's judged by a panel, and they have to bring their own money to it, but they have to actually win that this is significant enough research to warrant using this space.
What's the projected life expectancy of that lab?
I would say the way we built it now, it could last for longer than the building, right? 50 years. It's flexible enough that it can change, as long as there's not a major seismic event that shifts the rock. We'll be fine. Small seismic events are fine. Yes.
Yeah, Daryl, when the facility was originally built, I remember that there was a good effort put in to try to make it as flexible and usable for different experiments, because nobody knew exactly who was going to lease the space, and it's not like knocking down drywall if you want to put something else in there. How successful was it now in hindsight? Is there something that would be changed on the design to make it easier for research, or did we get it bang on kind of thing?
For the money that we had to invest, it's the best we could have done. There was a point where the researchers, a group of the researchers came to me and said, we have to add on this other space over here. There was a drift that we built so that you could actually extend the lab out to another area. And I said, well, we'll get it estimated. We estimated it was $2 million just to prepare that rough space. And so I said to him, I said, okay, he said, we got to do it. I said, okay. If you've got to do it, then that's fine. I appreciate that. But what are we going to take out of what we're building now, the $2 million, to do that? And then they met on it, and they decided they didn't have to do it that bad. So if you look at it, there was a lot of pain. I can tell you the first contract we let was the mining contract. And in the period of time between when we designed this, estimated it, and bid, nickel and copper went through the roof. There became, well, people were going in and ripping copper out of people's houses and everything. So that's in about that time frame. And so our mining contract doubled. Just the tender value doubled. And on top of that, we had to pay premiums to keep the miners, to keep this going. So right off the bat, I had a major hit on my budget. And so we began right immediately saying, okay, we were going to put all the services and all those drifts. Instead, we cut it back and said we're going to have all the services that they could ever need, and we're going to bring them to the start of the drift. Any researchers are going to attach to that and pay for all the services that go into their facility. Now, that was actually a good thing because we'd probably put the wrong service in. But now it's just a matter of the connection points are there, there's lots of capacity, you can connect whatever you want. So that's that flexibility. We ended up having more flexibility by having a challenge on the budget than we ever intended. And the researchers now say, well, this is great, this is more than we expected. So I've done a very good job of managing their expectations or something. Yes?
Were you able to recover heat energy from the mine exhaust to heat your building on the surface?
No, it's a little farther away. No, but the building on the surface, the problem with the surface is that it's like hard rock too, right? We had to blast to actually get a little bit to get the foundations in there. So there's not much capacity to sort of do things except bring it up in the air. We're right beside the helicopter pad where in an emergency, they bring the helicopter in, and in a strike situation, they bring the management in to run the place. And so we couldn't put anything above the ground either. We were just fortunate to get the piece of land, I think, very, very supportive. The ECO group, which is, I keep forgetting what they're called now. Anything else?
Excuse me, Daryl, did this extension simply add to the capability of the existing facility, or was part of the existing one decommissioned afterwards? Or?
Well, the areas of the old one, that like the room I showed you with the bubble, the sort of rough finish, ended up being more of a storage room. So all the spaces are there, but they were converted to others. And what this allowed the research group, the consortium, to do is expand the research into other areas that they couldn't do with just the original detector. This dark matter in the universe, they needed much more flexible space to start to manage the dynamics of, oops, that didn't work, we got to go in this direction with the research. So it really expanded their capacity to do a greater variety of research underground. And 30,000 square feet is not a bad piece of building. Anything else? Yes?
Personnel accommodations, you mentioned about events that would have the lab personnel confined within the lab for a period of time. How, like, is the place geared to accommodate them for a specific length of time period?
Well, yeah, well, they have washrooms. That's number one. They have, you saw they have a large industrial fridge and microwaves, no stoves, that sort of thing. They have laundry facilities. It's mostly to clean the clean lab gear, but that's what they're wearing when they're in there. They have actually compressed air brought in, so if there's a fire in the mine or an event that creates a lot of bad gases one way or another, then they'll turn on the compressed air and get breathing air through that rather than bringing it through the ventilation system. So they can stay there quite a while. There's lots of bottled water. They get hungry after a while because there's not that much food. But they've been stuck there for a couple of days. They don't like it. They call home, but through a landline. No cell phone coverage. They do have Wi-Fi.
The mix of a mining operation and a clean room wouldn't at all typically coexist under normal conditions. You may have mentioned this before, but is this, like the mining operation kind of made the whole thing viable because there's a revenue stream associated with it?
Well, the mining operation makes it viable because there's an elevator that's operating for the mine that they can use, right? And I'll take you to, there's another mine in the United States that's firing up. It's called the Grubstake Mine. And it's abandoned by the mining industry. And so if they go in there, they have to pay everything to run the elevators. They got to pay every nickel, right? And so this research lab in an active mine is the mine's running the elevators, they're running the ventilation system, and you're just taking your piece of it off there. As long as you don't interfere with the mining operation, they're happy to contribute to fundamental research, as I like to say. It's not the stuff that'll help you manage your buildings better, but it's fundamental to understanding the universe. And it's, I guess it's a necessary evil, right? But yeah, the mine, without the mine, it'd be very difficult to do this.
Anything else for Darryl? No? Excellent.
Oh, yeah.
I was just going to ask you, have they actually made any progress in determining whether dark matter exists?
Well, it's a bit early yet. So the units that I showed you there, they're like the small scale pilots for the bigger scale ones that'll go in the cube hull or the cylindrical hull. They call it the cryo pit. The reason why they call it the cryo pit is that they thought they were going to do like a cryo pit, right? And they may still do it to a certain degree, but it'll be sort of within a container, not the entire enclosure. But we designed it such there would be almost like blast doors that could be installed there if they put a gas in that could be life-threatening if it got out. Maybe it's not. Maybe the gas won't kill you, but the lack of oxygen because the gas displaces it does. And so we've built notches in the walls and the ceiling of it, so we could actually build those in if we needed to. So it's really about trying to set things up so you can adjust to where the research takes you. And I think it's so far they're pleased with it. I mean, eventually they're going to run out of space, right? And that's why you have to bid for the space and the time to do research, because they want to make sure it's good, solid-based research. They don't want people even that got money to waste the time underground, because it's very valuable. And it's really a landmark for Canadian research to even have this. It's the largest, deepest underground facility in the world. CLIMA.
So the people that lease a certain space in order to conduct an experiment, what happens when their experiment is completed? They disconnect and pull all their equipment back out again?
Yeah, unless they put in some infrastructure that would work for the next person, they would have to get it all out of there. Yeah, have to take it up to the surface. Yeah, they dismantle it, put it in those, well, they actually just put them on beds, I guess, to take them up, but they don't care about them being dirty anymore. But that was one of the things we had to do with the surface building, is build all these clean labs that could actually be where they manufacture the equipment to go underground. So a lot of it's manufactured right on site at the mine site. The equipment that actually goes underground and does the research.
When these people lease the space for research, I guess that goes back to the university, kind of recoup some of the initial investment?
No, it actually goes into the operation of the facility. So what they did is that the federal government grant gave them enough money to operate for, I believe it was a 5-year period of time, while they built their business case of the research that comes in will bring enough money to fund the composite operation of the facility. So that's how it's going to work. So it's the operation of it isn't Carleton's problem, isn't Queen's problem, it's this consortium's problem, which is kind of a separate entity. We still don't know who owns these facilities. That's a little bit of a gray zone. Apparently not. It's a consortium or one of the universities. I just don't want it to be Carleton.
Anything else?
Okay, Darryl, I gotta tell you, he thinks it's Dr. Evil who owns it.
Dr. Evil, dark matter in the universe.
Brilliant.
All right, a big round of applause for Darryl. Excellent presentation. So I'd like to thank Darryl for his time and his efforts here. Part of what we try to get with ASHRAE is a variety of presentations, and something like this with the depth of the technical knowledge is a real treat. So obviously with the quantity of questions it prompted, it was very interesting, and I'd like to offer him this gift, a token of our appreciation. Thanks very much.
Well, thank you.
All right, so that concludes our evening. Let me grab my notes here. Two things. I would ask you all to take a look at your email, and the next day you're going to be receiving a message that allows you to review the presentation. So it's a very quick online survey. Really helps us plan for years to come with what we want to present to the constituency. So take a couple of minutes to write that off. And the last thing, next meeting is third Tuesday of March. Speaker will be Jim Howard, and the topic will be lab exhaust. So we look forward to seeing you all then, and enjoy your evenings. Good night.